Comparative study of reinforced concrete frame building and RC steel composite frame building. Abstract: steel industry is growing in almost all parts of the world. The use of steel structure in construction industry is less in India as compared to USA, EU, and other developed countries. As well, cities in India are amongst high densely inhabitants per square kilometer, which restricts horizontal expansion, therefore vertical growth of building becomes predominant. Concrete structures are massive and bestow more seismic weight, while steel structure take more ductility and deflection. Composite construction consolidates the better properties of steel and concrete. In this study, the static analysis under the provision of IS 1893:2002 is carried out for three-dimensional models: RCC frame structure and RC steel composite frame structure with the help of ETAB software. Comparative study of RCC frame structure and RC steel composite frame structure for G+9 is included. Subject headings: Composite structures, steel structure, framed structure, seismic design, ETABs V18. 1. Introduction. In the past, for the construction, the choice was normally between a concrete structure and a masonry structure. Failure of many masonry buildings and multistoried RCC buildings due to earthquake have necessitated structural engineers to look for the different method of construction. Due to significant potential in improving the overall performance through rather modest changes in construction technology, use of composite frame structure is of particular interest. There is great potential for increasing the volume of steel in construction, especially the current development need in India. Use of steel, reinforced concrete, and composite steel concrete members which are functioning together. Such composite systems make use of each type of member in most efficient manner to maximize the structural and economical benefit. 2 elements of composite structure. 2.1 Shear connector. Mechanical shear connectors are required at the steel-concrete interface. These connectors are designed to a. Transmit longitudinal shear along the interface and b. Prevent separation of steel beam and concrete slab at the interface. There are 3 types of shear connectors as a. Rigid type, b. Bond or anchorage type, c. Flexible type. 2.2 Composite deck slab. Composite deck slab consists of composite column, encased hot-rolled I-section, steel beam, steel jacketing. 2.3 Composite beam. The steel beams are connected to the concrete slab in such a way that the two act as one unit. The beam is called as composite beam. Composite beams are similar to concrete T-beams, where the flange of the T-beam is made of concrete slab and the web of the T-beam is made of the steel section. 2.4 Composite column. It is a compression member consisting either concrete encased hot-rolled steel section embedded in concrete. At present there is no Indian standard code covering the design of composite column. The design method largely follows Euro Code 4, which provides latest research on composite construction. IS 11384-1985 does not make any specific provisions to composite columns. 3. Methodology. RCC and steel concrete frame models are analyzed. Seismic analysis of both RCC frame structure and composite frame structure are carried out using software tool ETAB V18. Different parameters such as shear force, story stiffness, story displacement, story drift are discussed. 3.1 Structural details. A typical plan of building is selected for comparative study of RCC and RC steel composite having plan dimensions 25 m x 16 m as shown in figure. 3D model is being prepared for the frame analysis of building in ETABs. Following basic parameters are used for analysis and design of structures. Results. Graph number 1 and 2 shows that the structure having steel beam with composite column shows more rigidity compared to RCC beam and column framed structure. The story displacement of model number 4 is 5% less compared to model number 1. Max story displacement differs in X direction and Y direction due to rectangular geometry and orientation of column. The permissible limit for displacement is h/500, where h is height of building. Total building height is 30.5 m. That means permissible limit for displacement is 61 mm. Permissible limit for story drift according to IS 1893, Part 1 2016 is 0.004 times the story height, which is 0.1220. All models are safe in drift criteria. Max story drift for all frame structure is within permissible limit. Story stiffness differs in X direction and Y direction owing orientation column. From chart 5 and 6 it is seen that, story shear for steel beam with composite column frame structure has reduced by 15% compared to that of reinforced concrete structure. Base shear for steel beam with RCC column frame is 16% less compared to RC framed structure. Conclusions. By keeping same specification and loading, we designed smaller section composite structure for the same bending moment, axial forces. Because of inherent ductility characteristic steel concrete composite structure under earthquake consideration, steel concrete composite structure performs better. As compared to RCC frame structure, steel beam with RC column frame structure and steel beam with composite column frame structure require less construction time due to quick erection of the steel beam and ease of formwork of concrete. Including the construction period as a function of total cost in the cost estimation will result in increased economy for the composite structure. Steel beam with composite column frame structure has less base shear, which gives economic foundation design. Construction period for steel beam with composite column frame structure is less. Also, requirement of construction worker is reduced. Also, due to inherent ductility of steel RC composite structure, it performs better in earthquake-prone region. According to analysis and my study on that, I conclude that steel beam with composite column frame structure is superior over RCC frame structure, steel beam with RC column frame structure, and composite column frame structure amongst all. Acknowledgements. Praise be to God who gave us life and provided species wisdom. I am infinitely thankful to God who helped me through my whole life. It gives me great pleasure to thank my guide, Professor J.P. Patankar, for their scientific support, accurate and consistent recommendations, and their tireless patience during the work of the project. I appreciate their deep knowledge and attention, as well as the encouragement he has given me throughout the entire project. I am grateful to the Department of Civil Engineering for giving us the opportunity to carry out this research, which is an integral part of the M.Tech curriculum at the Government College of Engineering, Carod. I sincerely thank all the Applied Mechanics Department professors. I also would like to thank those kind-hearted and helpful professors whom I met across my entire course. I would like to thank my classmates and friends for their continued help and encouragement throughout my entire M.Tech studies. Finally, throughout my life, I am extremely grateful to my parents, brothers, sisters, and relatives for their love, care, support, encouragement and prayers.